Number 40 and 4-1. Yep. So what's it say? Oh, okay. Find the critical number. So yeah, Jim. Critical numbers. What the hell are those? Where the derivative is 0 or? Huh? Sure. Oh, okay, okay. So critical numbers are where there might be a min or a max. So that would be where the derivative is 0 or where it's undefined. I like it. So critical number is a possible min or max. What else could it be? It could be one of these. I'm going to turn, no I'm not. Like you. Tricky function. Sure, yes? Like a cubic. Wouldn't be a true min or max. So critical numbers are where f prime of x equals 0 or f prime of x is undefined. All right. So number 40 says find the critical numbers, and you've got g of theta. This is 40 for real. Equals 4 theta minus tangent theta. That's going to be yummy. You guys should know when I say yummy, it's not the best. What is the derivative of this guy? Since the idea is to make this 0 undefined. 4
minus secant squared theta.
Kick ass. Is this prime means what? What does this prime mean in this case? So in other way to write g prime of theta.
0?
No. D theta. I like it. Because what is the independent variable in this thing? Theta. Theta is acting like x. Yeah, like it. Theta is not a constant, so we'll just believe that. So what do I do with this thing? Set equal to 0 or look for where it's undefined. Is secant undefined somewhere? Yes, wherever what is true? Wherever cosine is 0, because secant's 1 over cosine. All right, let me stop here for a second. None of what I said should be a problem. It should all be, okay, cool, I got you. Has to be, right? So let's look at where is secant theta undefined. It's undefined at theta equal to what? So really what you're asking yourself is where's cosine 0? Because secant is 1 over cosine. Yeah, so cosine is 0, pi over 2, and plus, does it give us any? No, just pi over 2, it's also 3 pi over 2, it's also 5 pi over 2. Where k is an integer. Alright, let me stop here again. That shouldn't be a problem either. You should be very used to that kind of thing. You should be crazy freaking trig functions. They kind of repeat. So secant, of course, what does secant look like? If you graph it, what does it look like? Looks like a bunch of parabolas just kind of floating in space. How do you graph secant? Well, you graph cosine, and then you put cups on the top and bottom of the hills and valleys. It's crazy. It's easy. Now, if you can't graph cosine, it's hard. If you can graph cosine, graphing secant is easy as shit, right? So it's going to have vertical asymptotes wherever cosine is 0. So that's what we found here. Where is 4 minus secant squared theta? Now what do I want to do with it? I want to set it equal to 0. Now what do these two correspond to? This is the one that we're really used to. Wherever it has this, that could be a max or a min, right? And that's horizontal tangent line at both of those. That's setting it equal to 0. The shit would this look like? How would this be a max or a min? Can somebody remember how is this slow? How is a derivative undefined? How is something not differentiable at a point? Ah, sweet. If it's a cuspy dude. So this guy would be like this. Cuspy dude. Is that a freaky point? Yes. Is a derivative like that point? No. Is that a max? Shit, yes. So that's why you got to include these. So the critical numbers are a list of all the x places where there might be a max or a min. So our next step immediately after talking about how to find them is how to test them. What is it? Or is it one of those things, aha, or it just keeps going up? It's like, oh, you. Okay, so how are we doing? That's what critical numbers are. They don't tell you anything yet. They say, something interesting might happen here. You're like, oh, okay. So I want to set this sucker equal to 0. That's this situation. I'm looking for where there's horizontal tangent lines now. How do I solve this shit?
Maybe we can add secant squared.
Okay, I like it.
And then we can square root secant squared with 4, and we get plus or minus 2 is equal to secant theta.
Kick ass. Which means plus or minus 1/2 equals cosine theta. Right? I know cosine better than secant. So why not write it in terms of cosine? Of course you could do that. I just flipped both sides. Right? And where's cosine equal to 1/2? Here's how I know it. Remember? Right. You know how to take a trig. Holy shit. But if you take in trig, see why this makes sense. Cosine likes x. It's biggest when it's close to the x-axis. So if it's at 30, it's going to be root 3 over 2. When is it? It's smaller and smaller. So 1/2 is the smallest option that we know before it goes to 0. Right? The ones you have to memorize. So it's got to be what angle then? Close to this. So it's got to be...
A 45 degree angle?
No, 45 is where it's rad 2 over 2.
Oh, wait, yeah.
5 or 3.
5
60 degrees. I like it. So this will be theta. Now it's plus or minus 1/2. Oh shit. So it's every. Yeah. Here's pi over 3. Where else is cosine positive 1/2? Where else is cosine positive? Fourth quadrant. So that would be negative pi over 3. Where is it negative 1/2? Because that's the other thing that this could be. Reference angle pi over 3, so this would be
2 pi over 3?
and it's also reference angle pi over 3, so this would be
4 pi over 3.
4 pi over 3. Okay. Aw, shit. How far apart are these? Pi. I like it. So I can capture those. How far apart are these? Pi over 3. I can't capture that in one statement. This is something you should know from trigonometry. I just wanted to remind you. Why do I need 2 statements here? Because I can't capture this and this, and then this and this, and then this and this. They're not equally spaced. These are, and these are. So you get pi over 3 plus k pi, or theta is, you could say 2 pi over 3 or negative pi over 3, doesn't matter. 2 pi over 3 plus k pi. So you get this and these. Oh man, I finished that problem. I was too excited. There you go. There's a problem for you. Didn't really mean to, but oh well. I just couldn't stop. And you're like, what the hell's wrong with you? I can stop way too easy. So yes, trigonometry will happen. I could teach calculus and have very little trigonometry in it, and then set you up for the hard brick wall of Calc 2 if you're going to take it. Right? It's like, that was nice, bam, you're dead in Calc 2, yes.
What isn't secant originally negative? So why can you square root it?
Say again, sorry?
Secant
Oh.
is negative.
Add.
Oh.
Yeah. Yeah, if it was 4 plus secant squared equals 0, that would have been no real answers. Right? I like it. And we're not dealing with complex Just realize everything we do could have complex stuff too. We just don't look at it yet. That's for later in your math career if you want to. Okay, cool. Anything else from homework stuff? So that was really, really good. That was a beautiful review of how to find critical numbers, what they really mean, and then a little trig review. Yes?
Can you do 19
For 2. This is that mean value theorem stuff you guys went over last time. So, who remembers, so mean value theorem? You guys talked about this last time, if you were here. Who remembers the basic idea of mean value theorem?
CK line with the 2 endpoints, somewhere in between that, the graph is going to have the same slope.
Sweet. So Rolle's theorem, hopefully she's talking about Rolle's theorem, is a specific case of mean value theorem. Mean value theorem basically says, if I have a continuous function that goes from A to B, however it looks in the middle, there's got to be some point C where the slope at C is the same as the slope from A to B. Let me say that again. How can you connect these two? I could just do a straight line. Then the slope everywhere is the same as the slope at any point inside of it. I mean, that's the easy case, right? Let's go straight to a weird ass case. So I can do like this, right? And then, so here's the slope as the crow flies. And what this theorem says is there's at least one location where the slope is parallel. So here I've got, it looks like 3 places, where the slope of the function is parallel to the slope between the 2 points. How does that look in a form that you can work with? What's the slope between the points? What's the slope of that line here? What's the slope of that line? You can do it. What's the slope of the line? y2 minus y1 over x2 minus x1. And the thing is saying that if you have a continuous, it's got to be continuous because otherwise you just bounce all over the damn place. You teleport. That's not fair. So it's got to be continuous, right? It says that the slope as the crow flies, there must be at least one location where the slope of the function itself is equal to that slope. They're parallel. So the base case is just, it's that freaking line. Then it's true everywhere. But the minute you start to turn away, you got to come back eventually to get there, right? That's the whole, I got to turn away and now I got to come back. Oh, somewhere you're going to be freaking parallel. So on one level, it's kind of like, duh. when you kind of see it and work with it a little bit, you're like, of course that's true. But it's based on if it's continuous. If it's not continuous, it can be whatever the shit it wants to. So this has got to equal the slope of the function at some point. So that's the basic idea of mean value theorem. I like it. Now I think, did you guys do? Oh yeah, okay. So this one asks you, this was number, what was this? 20? No, 19. Which one was it? 19. This one says, show that two x plus cosine x show it has one real root. And it doesn't tell you like on some interval or something, right? So what does it mean for a function to have a root? I mean, how can you show that this has at least one root? Is this function continuous? Yes, totally. It's made up of a line and a trig function. It's continuous on its domain, and its domain is everything. So it's continuous everywhere. What would have to happen for it to have a root somewhere s equals 0? Which way? This is linear, and cosine certainly goes through 0 a lot, right? I like it. So this doesn't have to happen, but one of the simplest ways to think about how to find if something has a root is it positive somewhere and then negative somewhere else? If something is positive somewhere and negative somewhere else and is continuous, it's going to have to go through 0. Now this has got another layer on top of it, because if I find, is everybody cool with what I just said? This should sound very familiar. So if I show that, like, at 1 this is positive and at 2 it's negative, then I know there's at least one root. But how many roots could there be between this and this? There could be an infinite number of roots. It could go, crazy. Okay, you guys, so this problem has an extra layer on it because it says show that it has one root. All right, so here's what's on top of this. Let me give you a little hint about this. If I knew that the slope was always negative from here to here, and then after this it was always negative, and past this it was always negative. So basically it was always negative. Wouldn't there be just one root? What's the only way you can have more than one root? If you go through and then come back. Do you see that? Uh-oh, just false. Do you guys see that? Is that? What if this has a root right here? What's the only way you can have another root? If it goes back up, which means the slope has to change. The slope would have to become positive. So there's another, that's what calculus is starting to allow us to do, to think about problems with that extra dimension of what's the slope going to do to make this happen. So if it's going to have only one root, one thing to check is what's the slope doing. So let me help you out a little bit. So this is your function you're dealing with. And you want to show that this function has a root. So when I'm talking about derivative, I mean the derivative of that. That's all I'm going to say. I'm going to give you that much of a hint. Who asked that question? Does that help you? Or no? Or did you already consider that?
Yeah.
You did? And what happened when he took us? It helped. Okay. Sorry, man. All right. Caffeine's a horrible drug, but man, it helps. Yes?
Okay, well, I know this is a dumb question, but I got stuck on section 3.11 on 23, and then get all asking.
Oh. All right, so I just want to remind you guys, section 311, I'm not going to make you memorize any of it. You still have to do the homework, but you can just reference the formulas. I really just, at this point, want you to know that hyperbolic stuff exists. It's built off of exponentials, which is why the derivatives are so nice. Is everybody kind of with me? A little bit. So this one, for example, the very first one. What's it say? X goes to infinity. What's the tangent? What's tangent? Tangent. Hyperbolic tangent. I want somebody to go, what's hyperbolic sine over hyperbolic cosine? Oh, yeah. Okay.
Tangent is sine h over cosine.
Sure. Okay, so tangent is sinh. Like, if I just ask directly for it, it'll happen. Now what's sinh? And what's cosh? It always sounds like somebody teaching trig, but also trying to shut a group of people up. Oh, shh. Yeah, shh. What's cinch? Yes. And my little, I finally pieced this together a while back. My little cosine is an asshole thing still works. Cosine takes the positive signs. So this is e to the x minus e to the negative x over 2. But isn't the over 2's going to cancel? Because this is also over 2. So basically, here's what it is. So in place of this, put this. Can you do the limit as x goes to infinity of this? Shit, yes. Totally. So every single one of those, rewrite it in terms of exponentials, because that's what they're all built off of. And the limits of these are easy. Is it okay for me to say that? What happens is I let this go to infinity. This piece goes to... No. Is e to the negative x. So it's 1 over e to the x. So as the x get really big, it's going to get really small. Come on now. Negative powers mean they're really on the bottom. If it's getting big, it's on the bottom, the whole thing's going to 0. Same thing with that. All right, this is after I put this in here. And then what's e to the x divided by e to the x? Okay, so that limit is 1.
Oh. So is that all it's asking?
Yeah. But hyperbolic trig functions, this isn't exactly true what I'm about to say, but you can look at it like this. They're just a collection of exponentials. It's a way to write, tanh is a way to write all this exponential shit in one little phrase. So when I have to work with this, very often what will I do? Write out what the hell it really is. I like it. All right. So if you go into this thinking you have to keep it like this and somehow you're supposed to figure this out, holy shit. No, you write what this represents. Work with that, because this is this. They're the same. So whatever this guy's limit is what this guy's limit is. That's how you do every single part of that. I like it. And Mikey. By the way, we're almost to L'Hopital's rule for those of you who are just waiting and hoping, and if you have no idea what the hell it is, you will like it once we do it.
I think I missed it when you talked about it, but what's the difference between a local and absolute?
Alright, I love it. I love it. So very cool with that. That was the section, that's 311, number 23, right? That one? Absolute max and min is awesome. It's easy shit. Local max and min, damn. So the difference is, if I tell you I have a function from A to B, and it does like this, is there an absolute minimum? Yes, and that's going to be at the location of a what? What is that? That is a what of that? It's a blank blank of the function. Critical point, critical number. I like it. You guys are like, there's too many blanks in there. You got to give us a little something. Where's the absolute max? And that occurred at the endpoint. So if you draw a few possibilities out, you'll start to realize that the absolute max or min is going to either occur at a critical number or at the endpoints. And absolute max means it's the biggest output. Absolute min means it's the smallest. So what do? If I give you a function and I ask you what's the absolute min and max, or I say what's the absolute extrema, a nice quick way to say min and max. Find the critical points. And I'm going to give you on some interval A to B. So we'll do an example here in a minute. So this kicks so much ass. I want you to realize it. If I say absolute, you go, oh, good. Because all you do is find the critical points. That's not difficult. And then you do f of the critical points, and you do f of the endpoints. And then you just see who wins. That's it. You just step back and see who wins. Yes?
So finding the critical points is basically the same thing as finding like the local maximum.
To find local max and min, you must first find the critical points. I like it. And an absolute max or min, it makes sense that it's going to sometimes be a local max or min, right? That's a local min, but it's also the absolute min. That's a local max, but it wasn't the absolute max. So it makes sense that critical points are a part of this. But the endpoints have to come into play also. I like it. What if one of my critical numbers was this number here? This is my critical point right there. What would I do with that? I would forget about it. It's outside the realm of what I care about. So could you get a critical point that's not in here? Of course, you throw that shit out. It's not in the race. It's too old or something. Whatever you want to think about. It's for little kids, dude. Get out of here. Oh man, kick your ass. Yeah. So let's do an example. Blah, 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 blah. Yeah, here we go. Yeah, that's boring. Here we go. Ooh, that's yucky. Let's see. Can't remember if I signed this one, but if I did, I'm happy with that. Alright, so this one says find the absolute min and max on this interval. Alright, take a minute and figure out the derivative. What do I need to get the derivative? Why do I need the derivative? To find the critical points. Equal to 0 and also see where it might be undefined. Alexandria. Melody. There you go. Steve. Roberta? Darren? Search party. Roman? Friends? Countrymen? Alright, let me catch up to you guys. Really cool. I like it. I made it nice. Is that what you guys got? Yep. So this is derivative of the top is 1 times the bottom minus the top times the derivative of the bottom. Now where's this thing equal to 0? Yeah, when the top is 0, 1 minus x squared, difference of squares, or whatever you want to look at it as, what two things do you get? 1 and negative 1. So at x equal 1 and negative 1. When would this thing be undefined? If the bottom were 0. Anybody see why I don't have to do any work for that? I know it can't be 0. At least not with real numbers. Kidding me?
Even if you put 0 in, there's still going to be a 1.
I don't care. Yeah, that's nice for you. But I mean, I could have a function where I can factor it, and the last number's positive, but that means I still have critical numbers, right? Or in this case, where it's undefined.
Right.
What do you check? I mean, can you factor them on? No, you can't factor that inside, right? You'd have to use quadratic formula to see where it's 0. What part of quadratic formula tells me if it's going to be real? B squared minus 4ac. Why would that have to do with it being real? Because that's the part that is under a square root, or radical. I like it. So b squared is 1 minus 4ac. 1 minus 4 is negative 3. No real places where this is undefined. There are complex places where it's undefined, but we don't care about that right now. We're talking about real shit. Nope. This is the place where understanding the stuff that was shown to you in pre-calculus helps you with calculus. You don't want that step to take you a long time. That discriminant thing is really helpful. When you look at, just go ahead and show me b squared minus 4ac, since it's under a square root, you can see if it's going to be complex or real or whatever. That's really useful. All right, so what have we got so far? What are we trying to find for this again? Critical points in order to find the absolute max and min. I like it. And the absolute max and min, when you see absolute, you go, oh, thank God. Because all you got to do is plug it in the function, see who wins. Now, some of you guys do not do this for yourself. You're going to hate yourself. You got to tell yourself what the shit the function is and what the derivative is. Some of you guys, and you're like, whatever, Jeff, you can yell at us all you want to. But I'm trying to help you. Some of you guys do things like this. X squared minus x equals 2x minus 1 equals 0. What the hell is that shit? Can anybody tease out what this really is? This was probably f of x. That means this is f prime of... What? So they're not equal to each other? And don't give me, I know what I mean. No. No, you don't. You're going to get to chapter 4. We're going to get into this graphing thing where you're going to be finding critical points from first and second derivatives. And you're going to be like, not only do I plug it in f prime, or f double prime, you're also going to be like, which one is which? I'm mean to myself. So don't do that shit. Tell yourself which is which. Because it's already hard enough to remember which one to plug it in. Like some of you guys saw last time. All right. So I got my critical points. Are both of them in the interval? No. Which one do I not have to worry about?
The negative one.
Yeah, negative one. Bleh. So what do I have to check? I have to check 0, so I've got to do f of 0. If I put them in f prime, why does that not have a thing to do with the max or min? It would tell me the slope at the endpoints. It doesn't tell me who's the highest and who's the lowest. That doesn't make any damn sense. Right? I mean, here. Yeah. I mean, what's the slope here? Positive, but this is an absolute min. So how do you tell it's a min? You got to know what the function output is. So of course you're going to plug these into the function, not into a derivative. I don't care what the slope is there. I want to see who wins. So f of 0, f of 3, and of course f of our surviving critical point. And then, like I said, it's really too nice to believe. You just see who wins. Who wins this prize and who wins that prize. One dude's going to be like, oh. So what's f of 0?
0.
0. What's f of 3? I don't know. Looks like 3 7s. What's f of 1?
1.
1? So what's the absolute min?
0.
Oh, yeah.
Absolute min is 0 at x equal to 0. To see how you can say it. What's the absolute max?
1.
Yeah, absolute max. Oh, get out of there. is 1 at x equal to 1. I like it. I like it. Absolute extrema are beautiful. They're awesome, though. They kick so much ass. Just going to see who wins. Okay. All right. So I want to, if there's no other questions, I want to focus on what about local maxes and mins? Because I keep saying that they're harder. Let's see, let's find one out here. Blah, blah, blah. Yeah, I like it. Oh, I know. Here we go. Perfect. So absolute extrema, nice. Local maximum, local extrema, a little harder. So local extrema. So for example, let's take one right out of here, blah, blah, blah. This one's not too crazy. That looks nice. Sort of going to be a review. We talked before about how to do this, but it's been a little while. All right. So what's the first thing I do? Right, I like it. That kicks a lot of ass. It's obviously not undefined anywhere, so all I got to do is figure out where it's 0. Right? Go ahead and figure that out real quick. By the way, what I normally do with these kind of questions is I'll give you a function and then I'll say verify that f prime equals this. Because if I didn't do that, if I just said find the critical points and you mess up the first derivative, you're screwed. The whole problem's going to go to shit. So if you can't get the derivative to work out, right, you can still do the rest of the problem. You just take the derivative I gave you. Does that make sense? So I'm trying to help you. Don't just go, I can't get that. Well, you got it. Do the rest of the problem. Lose points only on that one piece. How do I solve this? Yeah, take out 4x. So 4x, x minus 1, x plus 1. So my critical points are, critical numbers, 0, 1, -1. Now we have developed, I already showed you, remember what I said about finding the critical points are straightforward. I then have to test them to see if they're locations of maxes or mins. So the test that we use so far, we're going to learn a different test later, is the first derivative test. That's that sign diagram that we created. Why do we call it the first derivative test? Because what's the sign diagram going to show? The slope, which is the first freaking derivative. I love it. So you start to realize the importance of telling yourself what f is, telling yourself what f prime is, so you know which thing to use at what time. If I was trying to find a point to graph, what would I use? F of x. If I'm curious about the slope, I use f prime. Later today we're going to learn what the hell f double prime means physically, graphically, right? Okay, so this is officially called the first derivative test. I just call it making a sign diagram. So you put down there -1, 0, 1. What I do for myself, above it I would put a little u if it was an undefined slope, or a z if it's a 0 slope. So all of these are going to be z's. You don't have to do it the same way I do it, but to me that's the way that helps me out the most. What's true that's going to make this so much easier? What can I use? The idea of what? I really only have to find one thing, and then I can fill everything else in, because I can use the idea of multiplicity. I like it. Liquor, Jeff? Did you use No. Multiplicity. So put 1 billion in. Does everybody understand this sign diagram idea? What's the only way the slope can go from positive to negative is if it goes through 0 first, because the slope is continuous. So if I just put one number that's out here, if it comes out positive, it's positive for the whole damn time out there, because this is the only door near there that it could go through. So I look at those as doors. I'm kind of weird, but it just is a door to get through that wall that is the x-axis. Does that make a little bit of sense?
Yeah.
That's just weird me. So if I put 1 billion in, or if you put 2 in, it doesn't matter. They're both out there. Let's put 2 in there. It's easier to put it in this thing, to be honest. That's positive, positive, positive. So I get positive. So this is going to be negative, this is going to be positive, this is going to be negative. Because the multiplicity of each is 1. If you need to, plug in 1/2, negative 1/2, negative 8, or whatever, and you'll get the same thing I got, hopefully. I like it. So we went a little further than just finding maxes and mins. This kind of helps you really focus on why things are a max or a min. Can you tell me where this function is increasing? Careful, increasing.
It's increasing from...
Increasing means the slope would be positive.
So negative 1 to 0.
Negative 1 to 0.
Unity, or 1 to infinity.
And then it's supposed to be decreasing everywhere else.
Let's see, it's from...
All right, let me stop there. Everybody cool with that so far? Yeah. No. All right, so now underneath this, if I felt like it, I could make a little... Now what you could do is you could do this. You see what that does? That really makes it in your face about what's a min, or a max. How many mins do I have? 2 of them. What are the mins? Negative 1, something, 1 something. Now how do I figure out what that is? Plug it into f. If you plug it into f prime, what are you going to get? More specifically, you're going to get 0, because that's where the shit those came from, right? They made the slope 0, so guess what you get when you plug them in? You get 0. And when we get to the point where we start graphing this shit, your graphs are going to look funky as hell. Just make everything have a 0 output. There's my answer again. So, when you plug a negative 1 into the function, what do you get? 1 minus 2 plus 3. 2. And when you plug a 1 in, you get the same thing, right? Do you? Yes. This is nice. Symmetric, isn't it? Do you guys see that? What kind of symmetry does this function have? Odd or even? Even. Like x squared. It's going to be symmetric around the y-axis. All right, I like it. What about the max? 0? 3. Kicking acid. How did I know that was a min? Because look at it. I like that. I like that answer. Look at it. I don't know that's a max. It goes up to it and comes down from it. Of course it's a freaking max. Don't make more out of it. That's why this diagram is so useful. This is a rough graph of the sketch of the function. Do you guys remember that x to the 4th is the butt function? You guys remember that? Or depending on your teacher. I mean, it's a flipping butt. What do you want from me? Right? It's had some issues in the past. I don't want to talk about whatever medical condition. But it's a butt. So that makes sense. It ends up looking like that. But you can see it already. I already have a very rough sketch of this function. In fact, I can make it I can start to plot these points and make it much more detailed. Not very detailed, but much more than this. That's going to be section 4.3 and 4.5. It's going to be using the calculus work we did to make more refined graphs of functions by hand. Yes?
If you're just looking at a graph, local extremos can't be endpoints. Is that the thing?
So, local maxes and mins are where the slope is 0 or undefined. I can't talk about the slope at an endpoint. Yeah. Does that make sense? Because there's nothing going on past it. It's like, I know what the slope is going up to it, but what's the slope at that point? Well, can't really talk about that. That's why continuity has, I don't know if you ever noticed this, but they often have brackets, and differentiability often has parentheses, meaning you can't include those endpoints. Okay, maybe. But absolute maximum, yeah, they look at that. Yeah. All right. I like it. It might be. Okay. So, let's do this. Let's talk about the second derivative a bit. I'm going to give you a handout. Yay. So I'm almost certain that we talked about what the second derivative means a little bit before. This might be a good place to restart this.